Hello everyone, so welcome to lecture number 3. So today we are going to start our chapter 2. So in chapter 1 we talked about the introduction of colloids and surface, and in this chapter we will talk about the basic properties of colloids. So this second chapter you can see here, it's quite a long chapter because mm, four fundamental properties about to be discussed. So starting with the stability of colloids, and then the kinetic property, and then the electrical property, and lastly the optical property. So the optical property is basically linked with the characterization of colloids. Okay. And electrical property is also very important because it has several applications, and it is linked to electrokinetic phenomenon associated with colloids. Okay, so there will be several lectures to cover chapter 2. So today we start with this topic, that is to discuss how colloidal particles, mainly colloidal salts, are explained in terms of their stability. So how colloidal particles have been hypothesized to be stable in a dispersed medium like water. Okay, so we start with that. So while we talk about, or while we explain the reason for the stability of colloidal particles, we would definitely be talking about the different types of forces involved in the colloidal system. So for this, let's start with a system. So let's assume that our dispersion medium is liquid, and our dispersed particle, so like I am drawing it here, these are solid colloidal particles. So we can categorize this system as sol. Okay, so if you remember our definition in the introductory lecture, that if we have solid dispersed phase and or medium and liquid dispersion medium, we call it sol. So similarly, we are now talking about a system where we have particles dispersed in any liquid, maybe water, so we will see. So now the question is, what are the different types of forces externally working on those solid particles? Okay, so let's try to make a list of the different types of forces. So we can write that the colloidal particles are subjected to, okay, so following things. This could be some force or could be some motion. So let's see. So the first thing that comes to our mind, that as I talked earlier, that if you place some sand in the dispersion medium, they would automatically settle down by gravity. So therefore the first force that we can think of is the gravitational force. So we can write it here, gravitational force. Okay, so what does that force do? That this serves as a driving force for settling down. Okay, and suppose if a particle is settling down, the particle would settle down with some velocity, and that velocity we can call it the settlement velocity, or v subscript settle. So gravitational force, so let me correct that word, it should be gravitational force. Okay, so now the question is, what should be other kind of force. So remember, the particle is in liquid. Now even if the gravitational force pulling the particles down, so while coming down it must go through, it must make its way through the liquid molecules, right? And so the bulk liquid molecules won't let these particles easily go. So therefore the liquid itself, by their own inherent physical property, will exert some force uh, on these particles, so that would act against the settlement. Okay, so can you name that force? So that force especially is relevant because it is in liquid medium, is called the viscous drag force. Okay, so this viscous drag force is basically, we can tell that this is a resistance of settling motion, a resistance against settling motion. It actually offers any motion in the liquid, and if we are particularly interested in this the particles downward movement, along the gravitational pull, so we can call it that this works against the gravitational pull, or the against the settlement velocity direction. Okay, and the third thing, and it is a bit difficult to define the force exactly categorically, but since we are talking about colloidal particles, and in the first lecture I told you that there are some particular condition for a particle to be called as a colloidal particle, because there is some size restriction. In other words, if you remember their size range, so they are few nanometers to few microns. So basically these are very small particles. So whenever we have any small particles that are suspended in fluid means it could be gas, it could be liquid, then probably you have noticed, you think about some dust particle in air, these are suspended. So does the dust particle stay stationary in air? Obviously the answer is no. Or a pollen grain in water or in air. So what have you observed? That these particles actually move randomly in different directions. Okay, so this motion is a very typical one, and it happens once again due to some inherent physical properties of the molecules. So let's include that motion over here. So this is, we can call it that this is the natural kinetic energy of the molecules, or we can say, since this is, we are talking about some tiny particles, so natural kinetic energy of the particles that induces a random motion. And if you remember from your high school days, this is called Brownian motion. Okay, so you see the Brownian motion is very natural, and the few things are related with the Brownian motion. The one major thing is its thermal energy in the order of kT. K stands for Boltzmann constant, and T is the absolute temperature. So the ambient kinetic energy drives these molecules. It's basically a molecular phenomena, but can be extended to very tiny particles. So you see that when the particle is in under Brownian motion, and when it is showing a Brownian motion, it does not go in a particular direction as in a net manner. So it does not have a net direction of motion, but as long as it is showing the Brownian motion, it never settles down. Okay, so in other words, the particles under Brownian motion never settle. So these are the very important observation, and also the very important kind of forces that act on the colloidal particles. Okay, So now let's think about little bit bigger particles that are not under Brownian motion. Okay, so because you understand that the Brownian motion, the range of the size range of the particles are capable of showing Brownian motion is not a very wide range. So basically a vast range of colloidal particles do not have the luxury to show Brownian motion, so therefore they are mostly subjected to these two kind of forces. So therefore now we try to understand how these two forces act with each other for an individual particle. Remember, for an individual particle to stay afloat or to be involved in a stable colloidal suspension. Okay, so let's wipe the board and work that out through a mathematical equation. So here exactly I have posed this question, that how an individual particle that is not necessarily showing any Brownian motion can stay as a stable solid. So that means we are making a general statement for some kind of particle which has the ability to settle down because it is not showing any Brownian motion. So therefore from the very previous statements that we have just made, so there are two kinds of forces acting on that particle. So if we imagine that this is the particle and the gravitational force is pulling it towards the bottom of the container, so this force must be mitigated or must be balanced by some other force, and right now the only other force that we can think of, since this is in the liquid phase, that this is the viscous drag force. So remember, in air the viscous drag force is much less, so by gravity things can settle down, but in liquid the viscosity comes into a question, and that may provide sufficient resistance. Now let's see that how big the resistance is. So therefore for our individual particle to stay afloat in a stable solid, so we must say that the viscous drag force should compensate the gravitational force. Okay, now let's expand the expression for the viscous drag force. So from the Stokes law, this viscous drag force is defined something like that. This is 6 pi and v, and then we have radius and of the particle, assuming that it is a spherical particle, multiplied by eta. Eta is a constant and it is related to the viscosity of the liquid. Okay, so therefore this viscous drag force should be equal to the gravitational force. So how to define gravitational force? So gravitational force, or any force rather, this is mass times acceleration. So here acceleration is acceleration due to gravity, so that means mass times g, and here mass means volume multiplied by density and multiplied by gravitational pull. Now if we think that the particle is spherical, so the same r could define the volume 4/3 pi r cube multiplied by the density. Now here the only thing is the particle is actually inside the liquid, so that means we have to take care the buoyancy, the buoyant factor. So that means here the density that we are going to use, it should be the apparent density. So that means we would be assuming that this density is greater than the water, then only the particle would come inside the liquid phase, otherwise it would stay afloat, it won't be submerged. Okay, so therefore we have to tell that its density, whatever its density, it should be the density of the particle minus the density of water, then only it should be here. Okay, so we can express like that. So rho minus rho w multiplied by the acceleration due to gravity. Okay, so therefore we have 4 pi r, eta and v. So this v means the velocity of settling down, so we can directly write that this is the settlement velocity. So this is the critical limit. Okay, so if these two forces are balanced, then we have the particles floating in the liquid medium. So from this we can get an idea that what should be this critical limit of the V settlement, like beyond that the particle may settle down, or less than that particles stay afloat. So let's try to solve this V settlement. Okay, so if I try to solve it here, so you see we have pi cancels out, we have r here, so it leads to r square, and we have 2 here, we have 3 here, and we have 2. Okay, so therefore V settlement is equal to 2 divided by 9. We have r square, and we have rho minus rho w multiplied by g, and this thing whole divided by eta. All right, so this is the expression for V settlement. So now most common system is our water, so that means for water, okay, we can tell rho w is equal to 1. Okay, and if we call the rho w is equal to 1, so for water this thing becomes 2 over 9 r square rho minus 1 multiplied by g divided by eta. So if we fix the dispersion phase as water, so that means this viscosity coefficient, this eta, this constant, the constant for representing the viscosity coefficient is constant. Okay, and also acceleration due to gravity g is also constant, and this part definitely a number. So therefore we can write a very important observation that for a fixed for a fixed medium, how V velocity of settlement varies. So let's clean the board and let's write the statement directly from this equation. So now you see I have rewritten the same equation over here for water, because rho w is taken as 1. So therefore in water the settlement velocity is proportional to, because if we leave the constant matters out, it is proportional to r square multiplied by rho minus 1. So this tells me that the settlement velocity of any individual particle in a fixed medium like water is dependent on the radius and on the density. So V settlement means what? So the larger the V settlement value, okay, so that means the particle will settle faster. So therefore we see that larger, so we can write here that larger and heavier, because the density, if density is high, the particle will be heavier. So the larger and heavier the particle is, faster it would settle. And this is obvious, isn't it? The bigger and heavier particle will settle down faster. But we have made this visible by a mathematical equation, and it tells me that how on radius. So it is very sensitive on radius because it is dependent on r square. Okay, so therefore you see that for a stable colloidal sol, the density and the radius of the particle must be having a critical value or critical limit. So below that it can make a stable sol, and above that it cannot. So with time it would gradually settle down. Now another very important thing is that when the particles are very small, when the particles are very small, the Brownian motion dominates. So I will give you an example, then only you would understand that when to apply this equation. So therefore I'm just writing a small chart. Okay, so chart is the radius r. So I have a situation where r is equal to 10 nanometer versus r is equal to 10 micron. Okay, or rather 100 micron. So this is a kind of big particle, but both are under both are under the colloidal range. So then what I'm going to provide is the velocity. So the velocity is giving as in centimeter per second. Okay, and this velocity is nothing but the velocity comes from the Brownian motion. So that for 10 nanometer particle we observed it to be almost 100 centimeter per second. So can you convert into meter per hour? Okay, please convert and try to assess. And then for 100 micron this velocity becomes 10 raised to the power minus 4 centimeter per second. So you see how vastly the velocity in Brownian motion varies. So therefore whenever your particle is very small, okay, so Brownian motion takes care, so you don't have to worry about this equation there. Okay, and when the particles are bigger, so the Brownian motion does not dominate anymore, so then you have to worry about this equation. Okay, and so basically this one that would define depending on the dispersion medium, of course. But the most important thing, let me tell you once again, that all of these numbers, these Brownian motion numbers and this equation, we are applying on an individual particle. Okay, but as you know already, that this colloidal phase or sol is not about an individual particle. There is a collection, an assembly, a large number of particles. So there is still a big part is left, means a big question, that what happens when we start to think about the lot of particles and the interaction between the particles, or intraparticular interaction. So that really makes things very interesting. So for example, I start with, even though we have very small particles, say I have particles very small enough to exhibit Brownian motion, 10 nanometer, and I threw them in the dispersion medium, and with time what happened, that the individual particles start to attract each other, come together and make a big larger aggregation. Okay, and these larger particle would again defy the Brownian motion, because it would come to this region, and then again it would be so big, means r square value would become so big, it would dominate and it may settle down. Okay, so this was the very major question to explain the stability of colloidal medium, because up to this much was known due to the work of Debye, Einstein, Fick's, means the diffusion law. It was actually came from the Fick's diffusion law. So those scientists actually explain a lot of things, but still these equation not good enough to explain the colloidal stability, where we are not talking about an individual particle but a collection of many particles. Okay, so now we actually talk or address the question how to explain the colloidal stability even though particles are small. Okay, so let's do that. So in a stable colloidal suspension, stable means it has been standardized with the V settlement or Brownian motion, so means all other factors have been taken care. So particle size and particles density is good enough for them to be stable in the sol as an individual. But still, following forces do operate between individual particles. Okay, so first of all, let's list the first major force, and that is called the van der Waals forces. So remember I wrote it in plural, forces, because it is not a single force but it's a collection of many different types of forces. So what is the van der Waals forces? Probably you have heard about the different kinds of forces acting between molecules. So it's a part of an intermolecular force. So intermolecular forces or intermolecular attractions or repulsion can be of two types, that is non-covalent and sorry, the non-covalent forces are of two types, that is one is van der Waals forces and another is ionic forces or electrostatic forces. So here we are talking about the van der Waals forces. So this is the forces of attraction. So that means by which one molecule or one particle would always attract each other, and it is an universal force. So as long as there are solid condensed matter entity mass, the van der Waals forces would always be there and you cannot get rid of them. And there are three kinds of van der Waals forces mainly. Okay, so one is called the dipole interaction, means how the two water molecules attract each other. And remember, I'm still not talking about hydrogen bonding because it's a very special case. So neglecting hydrogen bonding, so there can be still dipole interaction, and there could be dipole induced dipole. So one is the polar molecule and another is a non-polar molecule, but still the non-polar may get induced polarity. And then there is formation of some instantaneous dipole. Okay, so now let's try to name these forces, because these forces have very special names according to some great scientists who contributed a lot to identify and made some equation to define these forces. So this dipole interaction, this force is known as the Keeson force. Okay, and the dipole induced dipole is known as the Debye force, and the instantaneous dipole is known as the London force, or it is also known as London dispersion force. So remember, you need two dipoles to have a dipole interaction. You need at least one dipole to have a dipole induced dipole interaction, but you do not need any polarity. So even like completely non-polar molecules like the iodine molecules, so how two iodine molecules attract each other is best described by this dispersion force or London dispersion force, where automatically some induced polarity is developed between the two non-polar molecules so that they get attracted to each other. And this London force or dispersion force is a universal force, and it is available, exist everywhere as long as there are a condensed matter concerned. Okay, so this is a very brief introduction about the van der Waals forces. Of course, you can read some basic physical chemistry textbook to know more about that. So the point of the major point is that van der Waals force is an attractive force. So it actually try to attract those colloidal particles together to make a large chunk, okay, means a large aggregate. So these van der Waals forces, I can write VDW, try to make them an aggregate. So that means few particles to make a larger single particles. So therefore it would act against the stability of the colloidal salt, because if many particles coagulate, they make a big particle and then they will settle down quickly. So therefore, to make these group of particles to form a stable salt, you need an opposing force, that is a repulsive force. Okay, so there you go. So the second type of force that we can think of, it is some repulsive force, and this time it actually comes from electrostatics. So an electrostatic repulsion force actually counterbalances these van der Waals forces. So that means what we can think about, that these individual particles are charged, means they have some charged surface. So we can assume that maybe they are having a negatively charged surface, and what would they do? They would definitely repel each other out, because the same charges repel, so they would try to stay away. So therefore these two forces actually balance each other out. So van der Waals forces try to bring them closer, electrostatic forces try to separate them. As a net result, they come into a compromise where all the particles, if individually they satisfy the conditions that I previously told you, they would form a stable colloidal salt. Okay, and you may wonder that, so that means whatever colloidal salt that we talk about, as long as in the dispersion medium, means water, mainly we talk about water, are they charged? The answer is surprisingly yes. So to make a stable colloidal salt, you need to have a charged surface. The moment you neutralize that surface charge, your salt phase is gone and all particles will settle down. And probably you will be surprised to hear that even an air bubble in water contains a negatively charged surface, although it has nothing to do with charge. There is no inherent charged particle on an air bubble. But there is also part of our discussion. We will tell you in due time that while talking about the surface properties, that not only air bubble but also the oil droplets in water would contain a charged surface. So remember, the existence of surface charge is very important for a solid, for a stable colloidal salt. Okay, so now you see there are different group of scientists explain the stability of colloids. So this is the central theory of the stability of colloids. Okay, and this theory is a Nobel Prize winning theory, because you can understand that this was not so easy to define. So a group of people, their name is, I can write their Jaguin, Landau, Warbeck, okay, let me check the spelling, whether I'm writing it, sorry, it is actually Warway and Overbeck. Okay, so a group of people, and there are four names, you see. So D for their Jaguin, L for Landau, V for Warway, and O for Overbeck. So together it constituted a theory. These days this is known as Dlvo theory. Okay, so this Dlvo theory basically explains the stability of colloids. Now, whatever I have told you is purely qualitative, okay, but in a very simple manner. Of course, I described the Nobel Prize winning theory in 5 minutes. So these people actually, with mathematics, they proved that what exact type and extent of forces you require the particles to form a stable colloidal sol. And as you know, that Nobel Prizes are not given just for anything. So their work had been recognized, and it is basically known as the Dlvo theory. So Dlvo theory of the stability of colloids. And the textbooks that I have shared with you, if you go through the pages, you will see detailed mathematical treatments are there. So if you are interested, you can go through the detailed mathematical treatment and the mathematical equation. But due to time constraint and the limitation of the syllabus, we are not exactly explaining this in detail. But you must remember that a Nobel Prize winning theory, Dlvo theory, explained the stability of colloids, and qualitatively this is the central uh, concept, that is, the van der Waals forces has to be neutralized by electrostatic repulsion force effectively. All right, so today we end here, and this was mainly the our first topic of chapter 2, that is the stability of the colloids. And so the in next lectures subsequently we will cover the kinetic properties, electrical properties, and the optical properties. So I recommend you to go through the textbooks as well as we go along, and I will see you in the next lecture. Okay, so till then, goodbye.